for staying, even though we're a bit behind on the time. So I'll be talking today about a known effect, but we wanted to put some magnitudes on this for different distances from shower axes, for different energies, for different zenith angles, and study the impact of neglecting or taking into account the asymmetries in the shower footprint in surface detector reconstructions, and also provide a parameterization for different detector types, which might be informative or perhaps even useful for different experiments. Okay, so just a quick review then. We've already seen a bit of information on this of how we measure extensive air showers. So of course the shower footprint arrives at ground on a surface detector array, and these particles then deposit signal. And what we typically do then is we plot the amount of signal, so the proportional to the number of particles more or less, deposited in each surface detector station as a function of the station's distance from the shower axis. So of course, the closer we are to the axis, the more particles. We then take the predicted signal at a specific distance from the shower axis, which in the case of an Auger-like detector is at 1,000 meters, this predicted signal, and we use that as our estimator for the energy. And I think on Thursday you can get a quick review about why we do this from Alan. So the aim here is, of course, to reconstruct the energy and arrival direction of ultra-high energy cosmic rays, as well as possibly their mass. And what we need to do this is, in between steps, is we need to reconstruct the shower axis, and we need to reconstruct the size of the shower, this S1000 I mentioned, which of course requires an estimate of the core as a stepping stone. And these are all important elements then for why asymmetries matter. So here, just as a schematic, we have a shower coming from the top right of our slide here, and this shower develops radially symmetrically around the shower axis. So if you pick any given distance from the shower axis on one side or the other side of the shower, you get more or less the same particle density. But of course, when the shower arrives at ground, as long as it's not a perfectly vertical shower, you're actually sampling the shower footprint at different points in the shower's development. So here we would have a later point of shower development in this station and an earlier point of shower development in this station. Now, of course, simple models then help us understand effects very simply. So here, if you put this in a schematic then, in a conical model, here we have an apex where showers are originating. Here we have the zenith angle of the shower. And then here we have these two detector stations. And again, here you have a longer distance to the downstream station and a shorter distance to the upstream station. And here we have the relative angles from the shower axis from this apex. So the first source of asymmetry comes from different amounts of atmospheric attenuation. So of course, if you have particles originating from the same point and they have to traverse a longer distance, more of them are absorbed in the downstream direction than in the upstream direction. And the amount of absorption and the amount of this relative difference between the two paths, of course, depends on if you have depends on the shower components, whether you have electrons and photons or if you have muons, which are less absorbed. So this decay constant changes. So this is one effect which would cause larger signals upstream than downstream. The second effect is if you have of course a different solid angle from the perspective of the apex. So if from the perspective of the point of particle production, and again this conical model, you look at the downstream detector, this downstream detector is further away, and objects that are further away of course look smaller. So this station would look smaller from the perspective of the apex than this station here. Additionally, the angle with which these particles arrive at these stations is slightly different. And if you were to project each of these stations into the plane defined by the angle of the arriving particles, then you would also have a different projected area of each of the detectors downstream and upstream. So this is another effect that would, again, in the end, give you more signal upstream than downstream. And then the last of the effects that cause these asymmetries relates to the angular distribution of these produced particles. So here we have a difference here, of course, in the angle, as I mentioned before, between the shower axis and then the trajectory of this particle to a given station. And you can see that if you have, and of course this relates to the transverse momentum of these produced particles, and if you have a narrower distribution, you would actually have less signal upstream than downstream. And if you have a wider distribution, this effect isn't quite as strong. But this is the one contribution that can actually give you an amplitude in the opposite direction of these asymmetries. So these are the three simple effects that we cover with this model here. And if you go through this conical model and you actually do some simple derivations, you more or less get an amplitude that's proportional to this formula you see here, which of course relates color-coded to each of the contributions to the asymmetry that we just talked about here. Okay, so then, of course, if you have a shower that lands on an array, the chances, and you measure for a given station, the chance of this station being at any azimuthal angle in the shower plane is equal for any given station that you have. So that means that if you have a shower that lands, you could have had the station land, or relative to the shower axis, be directly under the shower axis. You could have had the station be directly downstream from the shower axis, or anywhere in between. So here we have a schematic where all of these possible positions of the station in the shower plane, so these are all at the same distance in the shower plane, but the different angles xc in the shower plane. And what we typically see here, and this is just a schematic, let's not take the magnitude seriously for a moment, we'll get to that in a second. You can see that we see more signal upstream than downstream typically. This depends on where we are in the shower, but typically this is what we see. And in the electromagnetic component, where attenuation is really the dominant factor, you can see that this is driving this total asymmetry, because in at least for closer distances, we have more electromagnetic component than muonic component. In the muonic component, however, we often, in nearly our whole parameter space, we see a very small asymmetry, however, not everywhere, and we'll get to that just in a second too. But of course, the total asymmetry depends on the sum of the signal contributions from each of the individual shower components, and so what your fraction of muonic signal is in your total signal defines how much asymmetry you're going to have at a particular distance. Why does this matter again? So again, we come back here to our lateral distribution function, which we use to get this shower estimator. So if this closest station to the shower axis, or any station here, were to be downstream or upstream, it would have a signal that's, in this example here, say 20% higher or lower, depending on where you were in the shower plane. So this can influence your reconstruction, and of course that's something we wanted to quantify. But in general, if you don't take into account these asymmetries, and you just run a reconstruction assuming a radially symmetric LDF, you can see that you shift your shower core for, again, Auger-like array for energies 10 to the 18.5 and above. You see a shift of about 40 meters in the upstream direction. So again, upstream stations have more signal. The reconstruction mistakes higher signal as being closer to the shower axis, and this is the bias that you then get. So then we, of course, wanted to build a model and parameterization for this, as mentioned. So what we did then is we simulated a number of dense rings at different distances from the shower axis. What is a dense ring? It's just stations that are equally distant in the azimuthal angle in the shower plane, xc. And we did this for different distances. And then what you can do is you can fit a simple cosine. I just wanted to show here, which again falls out from this conical model as the first order approximation for the asymmetry, and it fits rather well. So then we look at the amplitude of this asymmetry, the amplitude of this cosine in the signal at different parts in our shower. Okay, so that's the simulations we ran. We ran them for a few different hadronic interaction models, energies at the highest energies, and up to 60 degrees zenith angle, and for two different types of detectors. Because of course, how sensitive you are to different shower components depends on your detector. Okay, so here's generally what we see as a function of distance. So here we have the amplitude of the asymmetry as a function of distance from the shower axis. What you see is that close to the shower axis, you have a quick increase of the amplitude, and then we get some flattening behavior at larger distances from the shower axis. Of course, what's also striking, and what would be expected then, is that for less inclined showers, your amplitude is much smaller than for more inclined showers, because the relative amount of attenuation between downstream and upstream stations scales with your zenith angle. So this is what we see. Up to about 500 meters, you have this increase in amplitude, and then beyond 500 meters, more or less, you get this sort of flattening, although where this flattening takes place seems to depend also a bit on zenith angle. So breaking this down a bit to try and understand it some more, you can again plot amplitude as a function of distance once more, but now splitting up the electromagnetic and the muonic components to the signal. And what you see for these downwards facing triangles here is that you see the electromagnetic component has a monotonically increasing amplitude with distance when you have a higher relative attenuation between downstream and upstream stations. However, the muonic component has an amplitude which is very small, even at large zenith angles, and even becomes negative. And there you see this last source for the asymmetry come into play, which is this angular distribution of produced muons, which can actually give you an asymmetry in the opposite direction. Now, of course, as you move from distances closer to the shower axis to further from the shower axis, your fraction of signal coming from muons increases, and therefore you get this flattening behavior that we saw in this previous slide. Oops. Okay, so then just comparing how this manifests in different detectors. Scintillators are, of course, more sensitive to the electromagnetic component of air showers, so they're more sensitive to these asymmetries, and water Cherenkov detectors. So what you see as a function of sine squared theta here for the amplitude of this asymmetry is something that peaks out at about 0.4. So that means you have 40% more, amplitude of 0.4. So really you have even 50, if you have massive asymmetries between downstream and upstream stations. But then it decreases because, again, at larger zenith angles, you have the muonic component that begins to dominate, and so there you get this reversal of the amplitude of this asymmetry as the electromagnetic component dies out. And you see that in both detectors, but the point at which you peak is much higher for the scintillator and at all different zenith angles. Okay, so how does this matter for the reconstruction? Last few slides here. So here, taking into account just reconstruction based on water-Cherenkov detectors, again with an OJ-like array. You can see this core bias that was previously mentioned of about 40 meters. So here we have the core bias as a function of the size of the shower. And this is pretty much universal for the different shower sizes that we studied. However, as the amplitude of the asymmetry increases with zenith angle, you also see that the core bias increases with zenith angle. And for 60-degree showers, you can even have a core bias of around, say, 60 meters or so. Applying this asymmetry now, these filled markers, you see that this core bias is corrected. Thank you. So here we have the resolution on the core, and this is also here plotted as a function of the shower size. And here you do see a difference as well. So you got a correction of the bias, and you also see that the resolution increases or improves by about 50%. So here you get a resolution of, say, 60 for these large showers in meters, and here your resolution is dropped to about 40 when applying this correction, and you see something similar as a function of zenith angle then. Okay, and then here what we had hoped, of course, is that you also improve on your resolution of the shower size. This doesn't seem to be the case with the studies that we performed. Neither the shower size resolution nor the resolution in your angular reconstruction changes much, nor do you see a significant bias when not taking into account these asymmetries and taking them into account. You see biases that are very small, and so this doesn't seem to be important for getting an unbiased shower size. Nor arrival direction. The reconstruction compensates very well, even under a radial assumption, by shifting the core such that you don't get a bias in your shower size. Okay, and that brings me to my summary. Again, we see asymmetries that have amplitudes of up to 25% for water-Cherenkov detectors, 40% for scintillators. And this is an interplay between a number of different effects that we've discussed. It induces biases in the core position if it's not properly taken into account. And we get an improvement in the core resolution and in the bias in the reconstructed core if you do take it into account. Now for details, including the functional forms of these parameterizations as a function of energy, or rather shower size, zenith angle, distance from the shower axis, so the functional forms and parameterizations for the two detectors, you can see the proceeding that will be written in relation to this talk. So thank you.